Hello and welcome back to GK and Coding Hub. I'm Advait and today I will tell you about dark energy and dark matter. First we'll learn about dark energy and then we'll head to dark matter. So let's begin. Dark energy. In physical cosmology and astronomy, dark energy is an unknown form of energy that affects the universe on the largest scales. The first observational evidence for its existence came from measurements of supernova, which showed that the universe does not expand at a constant rate. Rather, the expansion of the universe is accelerating. Understanding the evolution of the universe requires knowledge of its starting condition and its composition. Prior to these observations, it was thought that all forms of matter and energy in the universe would only cause the expansion to slow down over time. Measurements of this cosmic microwave background suggest that the universe began in a hot Big Bang in which general relativity explains its evolution and the subsequent large-scale motion. Since the 1990s, dark energy has been the most accepted premise to account for the accelerated expansion. As of 2021, there are active areas of cosmology research aimed at understanding the fundamental nature of dark energy. Assuming that the lambda CDM model of cosmology is correct, the best current measurements indicate that dark energy contributes 68% of the total energy in the present-day observable universe. Einstein's cosmological constant. The cosmological constant is a constant term that can be added to Einstein's field equation of general relativity. If considered as a source term in the field equation, it can be viewed as equivalent to the mass of empty space, which conceptually could be either positive or negative or vacuum energy. The cosmological constant was first proposed by Einstein as a mechanism to obtain a solution of the gravitational field equation that would lead to a static universe, effectively using dark energy to balance gravity. Einstein stated that the cosmological constant required that empty space takes the role of gravitating negative masses which are distributed all over the interstellar space. Inflationary dark energy. Alan Guth and Alexei Starobinsky proposed in 1980 that a negative pressure field similar in concept to dark energy could drive cosmic inflation in the very early universe. Inflation postulates that some ripples of energy, qualitatively similar to dark energy, resulted in an enormous and exponential expansion of the universe slightly after the Big Bang. Such expansion is an essential feature of most current models of the Big Bang. However, inflation must have occurred at a much higher energy density than the dark energy we observe today and is thought to have completely ended when the universe was just a fraction of a second old. It is unclear what relation, if any, exists between dark energy and inflation. Nature of dark energy. Dark energy is thought to be very homogeneous and not very dense, and is not known to interact through any of the fundamental forces other than gravity. The reason dark energy can have such a profound effect on the universe, making up 68% of universal density, in spite of being so dilute, is that it uniformly fills otherwise empty space. According to general relativity, the pressure within a substance contributes to its gravitational attraction for other objects just as its mass density does. Thus, this happens because the physical quantity that causes matter to generate gravitational effects is the stress energy tensor, which contains both the energy and density of a substance and its pressure. Now we'll learn about dark matter. Dark matter is a hypothetical form of matter thought to account for approximately 85% of the matter in the universe. Its presence is implied in a variety of astrophysical observations, including gravitational effects that cannot be explained by accepted theories of gravity unless more matter is present that can be seen. Dark matter is called dark because it does not appear to interact with the electromagnetic field, which means it does not absorb, reflect, or emit electromagnetic radiation, and is therefore difficult to detect. In the standard lambda CDM model of cosmology, the total mass energy of the universe contains 5% ordinary matter and energy, 27% dark matter, and 68% of a form of energy known as dark energy. Thus, dark matter constitutes 85% of the total mass, while dark energy plus dark matter constitutes 95% of the total mass energy content. Early history of dark matter. The first to suggest the existence of dark matter using stellar velocities was Dutch astronomer Jacobus Kapteyn. Fellow Dutchman and radio astronomy pioneer Jan Oort also hypothesized the existence of dark matter in 1932. In 1933, Swiss astrophysicist Fritz Zwicky, who studied galaxy clusters while working at the California Institute of Technology, made a similar inference. He applied the virial theorem to the Coma cluster and obtained evidence of unseen mass he called dark matter. In the 1970s, Vera Rubin, Kent Ford, and Ken Freeman's work in the 1960s and 70s provided further strong evidence, also using galaxy rotation curves. Rubin and Ford worked with a new spectrograph to measure the velocity curve of edge-on spiral galaxies with greater accuracy. This result was confirmed in 1978. An influential paper presented Rubin and Ford's result in 1980. They showed most galaxies must contain about 6 times as much dark as visible mass. Although both dark matter and ordinary matter are matter, they do not behave in the same way. In particular, in the early universe, ordinary matter was ionized and interacted strongly with radiation via Thomson scattering. Dark matter does not interact directly with radiation, but it does affect the cosmic microwave background by its gravitational potential, mainly on large scales, and by its effects on the density and velocity of ordinary matter. Structure formation refers to the period after the Big Bang when density perturbations collapsed to form stars, galaxies, and clusters. Prior to structure formation, the Friedmann solutions to general relativity describe a homogeneous universe. Later, small anisotropies gradually grew and condensed the homogeneous universe into stars, galaxies, and larger structures. Ordinary matter is affected by radiation, which is the dominant element of the universe at very early times. As a result, its density perturbations are washed out and unable to condense into the structure. If there were only ordinary matter in the universe, there would not have been enough time for density perturbations to grow into the galaxies and clusters currently seen. Dark matter provides a solution to this problem because it is unaffected by radiation. Therefore, its density perturbations can grow first. The resulting gravitational potential acts as an attractive potential well for ordinary matter collapsing later, speeding up the structure formation process. Hope this video gave you a glimpse into dark energy and dark matter. If you found this video helpful, please leave a like and subscribe to the channel for more such videos.